Hello everyone, this is Henry from Queen's University in Canada. This is a collaboration work with Zhiyin Zhang from Microsoft. This work is about predicting the receivers of football passes. This work is under the Prediction Challenge program of this workshop. Football is a highly collaborative team sport. Passing the ball to the right player is essential for winning a football game. For example, here, the player number 10 in the red team is controlling the ball, and the player has multiple options to pass the ball to his teammates. And in this work, so we want to build a model to predict the receivers of the football passes. First, let's look at our dataset. Our dataset has over 12,000 football passes performed by our Belgian football club in 14 games. For each pass, the dataset contains the coordinates of all the players, the identifier of the sender and the receiver of each pass. When we look into the dataset, we find the overall passing accuracy is 83%, which means in 83% of the cases, the players pass the ball to their teammates, but in the other 70% of the cases, they pass the ball to the other team. So we also divide the pitch into 3 equal-sized fields: the back field, the middle field, and the front field. We find that the passing accuracy is decreasing from the back field to the front field, from 86% to 79%. We also find that the median passing distance is 40 meters for all the passes, and 75% of the passes are within 20 meters. And when we look into each field, we find that the passing distance is decreasing from the back field to the front field, from 70 meters to 11 meters. We find that overall players pass the ball forwards in 62% of the passes, and in the backfield, the players pass the ball forward in 74% of the cases, which is decreasing to middle field and front field. In the front field, players only pass the ball forwards in 50% of the cases. In order to predict the receiver of a pass, we extract 5 dimensions of features. These 5 dimensions of features capture the sender's position, the candidate receiver's positions, the passing path, the team position, and the game state. Overall, we capture 54 features that fall into these 5 dimensions. The sender position features capture the position of the sender, that is the player who is passing the ball, such as the sender's distance to the goal line of the other team, and the sender's distance to its opponents. The features in the candidate receiver position dimension capture the position of the candidate receivers, such as the receiver's distance to the sender and the receiver's distance to their opponents. The features in the passing path dimension capture the quality of a potential passing path, such as the passing angle of the passing path and the distance of the opponent players to the passing path. And the features in the team position dimension capture the overall position of the team in controlling of the ball, such as the front line of the team position. The game state features capture the status of the game, such as the starting time of a pass. We do not include the ending time of a pass as our feature because it includes the information about the duration of the pass. In this work, we formulate the task of predicting the receiver of a pass as a learning to rank problem. A learning to rank model predicts a ranked list of candidate receivers based on the probability of being the right receiver. For example, here, the player number 10 in the red team is controlling the ball. A learning to rank model may predict that the number 10 has the highest probability to pass the ball to number 11 in the red team, and then with the second highest probability to pass the ball to the red 9, and the third highest probability to pass the ball to red number 7. In this work, we use the light GBM model to rank the candidate receivers. The light GBM model is a highly efficient gradient boosting decision tree. Using the 5 dimensions of features as the input, the light GBM model can predict a ranking list of candidate receivers based on their probability of being the right receiver for each pass. We use a tenfold cross-validation to build and evaluate our model. First, we randomly divide our dataset into 10 equal-sized subsets. In each fold, we build our model using 90% of the dataset, and we use the rest 10% as the testing data. We repeat this process until each of the 10 subsets are used as testing data once. Within the 90% of the model building data, 80% of the data is used for training the model, and the 10% of the data is used for tuning the hyperparameter of the model. Instead of using only one set of hyperparameter values, we get the top 3 sets of hyperparameter values. Then we build 3 models using these 3 sets of hyperparameter values. And our final output is the average of the output of the 3 models. By using such an ensemble approach, so the performance of our model can improve by 2%. We use 2 metrics to measure the performance of our model. The first metric is the top n accuracy, which is the accuracy of the model's top n recommendations. It is the probability that the correct receiver is within the top n predicted candidate receivers. The second metric is the mean reciprocal rank, or MRR. Let's first look at what is reciprocal rank. It is the inverse of the rank of the correct receiver in the predicted candidate receivers. For example, if the correct receiver is ranked as the 5th in the predicted ranked receivers, then the reciprocal rank for this pass is 0.2. The mean reciprocal rank is the average reciprocal ranks over all the passes. In order to evaluate the performance of our light GBM model, we also derive 3 baseline models. The first one is the random guess model, which selects the receiver by a random guess. The second one is the nearest pass model, which predicts the nearest teammate of the sender as the top candidate receiver. The third one is the nearest forward pass model, which predicts the nearest teammate of the sender that is in the forward direction as the top candidate receiver. This figure compares the performance of our light GBM model with the performance of all the baseline models. Here we exclude the false passes which pass the ball to the other team. Here the blue color shows the performance of our light GBM model. The top 1 accuracy is 50%, the top 3 accuracy is 84%, and the top 5 accuracy is 94%. And the MRR is 0.68. Our light GBM model outperforms all the baseline models. Among the baseline models, the nearest pass model, which rank the closest teammate as the top ranked candidate receiver, performs the best. This figure compares the performance of our light GBM model with the performance of all the baseline models when we also consider the false passes which pass the ball to the other team. The blue color also shows the performance of our light GBM model. Our light GBM model still outperforms all the baseline models with a top 1 accuracy of 41%, a top 3 accuracy of 70%, top 5 accuracy of 81%, and an MRR of 0.58. This figure shows the performance of our light GBM model for the passes in the different parts of the pitch. We find that our model performs better for the passes that start from the backfield and the front field, and the model performs worse for the passes start from the middle field. It is possibly because that a player who passes the ball in the middle field has more options than the players in the back and front field. We also analyze the importance of the features in our model. We find that the most important features capture the candidate receiver's positions relative to the sender and their opponents, such as the distance from a candidate receiver to the sender and the distance from a candidate receiver to the opponents. Passing the ball to the right player is essential for winning a football game. In this work, we build a model to predict the right receiver of a pass. First, we extract 5 dimensions of features from the dataset in order to explain the receiver of a pass. Then we use the light GBM model to rank the candidate receivers. Our light GBM model achieves an accurate performance, which outperforms all the baseline models. This is my contact. Please reach me if you have any questions or if you want to talk to me. Thank you very much.